The trapezium rule is a way to estimate the area under a curve, using shapes instead of finding an exact integral. It works by fitting a series of trapezium shapes underneath the curve, side by side, and adding up their areas. In words, the trapezium rule formula is half of the strip width times the sum of the first and last function values plus twice the sum of all the middle function values. In symbols, that is, integral of f of x dx is approximately equal to h divided by 2 times, open bracket, f of x naught plus f of xn plus 2 times the sum of the middle f values, close bracket. Let us work through an example. We will estimate the integral of x squared from x equals 0 to x equals 2. We will use 4 strips, so the width of each strip, which we call h, is 2 divided by 4, which equals 0.5. Now we find the x values at the edges of each strip. They are 0, 0.5, 1, 1.5, and 2. At each of these x values, we work out f of x, which is x squared, giving us 0, 0.25, 1, 2.25, and 4. Here is the 2D view of the curve with the trapezium strips drawn underneath it. Now we transform this into a 3D view where each trapezium becomes a solid slab, so you can see the same shapes from another angle. The caption updates in place to show 3D view of the trapezium strips. Now we substitute our values into the formula. The first and last function values are 0 and 4, and these add together to give 4. The middle function values are 0.25, 1, and 2.25, and these add together to give 3.5, then we double this to get 7. Adding these two parts together, 4 plus 7 gives us 11. Then we multiply by half of h, which is 0.25. This gives a final estimate for the area of 0.25 times 11, which equals 2.75. Now, for the check step, the exact value of this integral, found by proper integration, is 8/3, which is approximately 2.667. Our trapezium estimate of 2.75 is close to this true value, and using more strips would bring the estimate even closer. Now let us look at Euler's method. Euler's method estimates the solution of a differential equation by taking small steps, one at a time, using the slope of the curve at each point. Instead of finding an exact formula for y, we build up an approximate value, step by step. In words, at each step, the next y value equals the current y value plus the step size times the slope at the current point. In symbols, that is, y sub n plus 1 equals y sub n plus h times f of x sub n, y sub n. Here is our worked example. We are given that dy by dx equals x plus y, with the starting condition y equals 1 when x equals 0. We will take one step using a step size of h equals 0.1. At the start, x naught equals 0 and y naught equals 1. The slope at this point is x naught plus y naught, which is 0 plus 1 equaling 1. So our new estimate is y1 equals 1 plus 0.1 times 1, which equals 1.1. Now for the check step. We repeat the process using two smaller steps of h equals 0.05 instead of one larger step. For the first small step, the slope at x naught, y naught is 0 plus 1, equaling 1, so y1 equals 1 plus 0.05 times 1, which is 1.05. For the second small step, the slope at x1, y1 is 0.05 plus 1.05, equaling 1.1. So y2 equals 1.05 plus 0.05 times 1.1, which equals 1.105. The true value of y at x equals 0.1, found from the exact solution, is approximately 1.1103. Notice that using two smaller steps gave 1.105, which is closer to the true value than the single larger step, confirming that smaller steps make Euler's method more accurate.